Steltner, postdoc also in Hanover, and I'll present the results of the Einstein Home all-sky search for continuous gravitational waves. So luckily I can skip quite a lot here, so let cherry pick my introduction a bit. I think one important distinction is I'll talk about continuous waves in the LIGO band, so above 20 Hz, so not PTA or LISA sources. We already heard the most promising emission mechanism are probably these non-axis symmetric fast-spinning neutron stars, which have like a bump, not aligned with the spin axis. So there are other emission mechanisms which I, however, will just ignore. They have not yet been detected, and this is mostly due to the reason that the gravitational wave amplitude of the continuous waves is orders of magnitude lower than the detected CDC events, which makes sense since the masses involved are also so much smaller. However, compared to the CDC events, they are long-lasting, on the order of months to years to whatever, as long as this mass asymmetry is sustained and the neutron star keeps spinning. So to make up for that, we can integrate lots of data to accumulate the necessary signal-to-noise ratio. So since these signals are so weak, we use this match filtering, which Lucia already mentioned, which is basically convolving a signal waveform with the data. So we throw a template at the data, and if it matches some detection statistic, gets excited. If it only matches a bit, it gets less excited, and if it does not match, it's totally unfazed. I wish we wouldn't have numbers, but emojis at the end of our time. So our signal waveform, already mentioned. Just let me briefly say something about the sky, the all-sky searches. The sinusoidal signal is Doppler modulated, so really every sky position, our waveform looks different. And on the time span of the observation runs, like half a year or a year, there really are a lot of waveforms resolvable. Or the other way around, if we want to search over it, we need to throw a lot of waveforms at our data to find anything. So actually, our continuous wave searches are computationally quite intensive and computationally limited. And how intensive depends on the amount of target information we had. We've already heard the targeted searches. We know a pulsar electromagnetically. We know where in the sky it is. We know the frequency evolution. It's basically a single template search, maybe within a small uncertainty. You can run it on a laptop. It's quite fast. It's quite sensitive. However, if we look at a directed search, which Jing will talk the following talk about, we target supernova remnants, for example, so possible neutron stars. So we know when the sky it is, but not the frequency evolution. It's already quite expensive, and since we're computationally limited, less sensitive. And in the end, if we don't know anything about our sources, so it's anywhere in the sky, any frequency evolution, this is quite expensive. We need computer clusters, etc., and it's the least sensitive search. Let me just highlight that in this talk, I'll talk about isolated sources, so neutron stars without a binary, without a companion, because this would add orbital parameters, which would make it even more expensive and thus less sensitive. Anyway, all-sky searches are amongst the most computational intensive gravitational wave searches, so one could ask the question, why go to the trouble of an all-sky search? You know this better than I am, but there are 3,300 pulsars or more than that known electromagnetically, but depending on who you ask, there could be 10 to the 8, 10 to the 9 neutron stars in our galaxy, which is sort of our range, which are sort of hidden from electromagnetic observers, so it's a very rich population of targets. Let me quickly say something about our search technique. Actually, a coherent search for continuous waves is computationally infeasible, with which I mean that we match all the waveforms to the full time span of data, because the necessary resolution grows with the high power and the time span. So instead, we are doing semi-coherent searches where we divide this whole time span of data into a number of segments of occurrence time Tco, analyze each segment coherently, and combine the detection statistic as some average over the segments. This is less sensitive than the coherent search, but the computational cost now is the number of segments times the same power of the smaller T-code, which is way less than time span. So this is also important for Jinx talk, so remember this. Semi-coherent searches are less sensitive, but way cheaper, and therefore make continuous wave searches affordable. Okay, now that I covered all that, let's come to the actual search. We did a search for continuous waves in the gravitational wave frequency from 20 to 800 Hertz. This spin down and all over the sky without binaries. And we used the first half of the third observation run of advanced LIGO, so-called O3A, so 6 months, and to cover this parameter space, a total of 7 times 10 to the 18 waveforms were necessary to cover the parameter space. If we would have run that on one GPU, sequentially, we would still basically wait 2,200 years for that to finish. So, I mean, I want to grow those old, but we need to publish papers fast, so we utilized Einstein Home and Atlas to equal parts, where Einstein Home is a distributed volunteer computing project where volunteers, you and me, can basically click on the button, download the Bonn client, and every time the phone, laptop, or PC is idle, it runs a part of our search, which is a quite great resource to have. And the Atlas computer cluster is a supercomputer down in the basement of our institute. And with that, it was possible to run this search in 1 real year, basically. So I could go, and I would like to go into the details of how to set up such a large survey, how to handle it, etc. But yeah, probably not that interesting here. So let me just say with some clustering methods, out of these basically 10 to the 19 waveforms, let me round up a little bit, we identified the 3.5 million most promising regions in the parameter space. We did this with large-scale Monte Carlo studies of fake signals put into the data, treating them exactly as a real search, also quite expensive, but that way we know how a real signal would show up in our data. And with this 3.5 million candidates, we then went into a hierarchical follow-up, so this 3.5 regions, or whatever you want to call it, and basically went through multiple stages, where each stage is a more sensitive search. And at the end of stage 7, where we are fully coherent in the O3A data, so only one segment basically, we then went to O3B, the second half of the O3 run data, which we not yet have touched, which is very great for cross-checking, since if the signal is in O3A, it should also be in O3B. And then also did the search in O3A plus B combined, because why not? And in the end had only 6 survivors out of this 3.5 million candidates. And these 6 survivors were 6 of the 7 hardware injections, where hardware injections are fake signals put into the detector at the hardware level by actually moving the mirrors, which is really great for pipeline validation purposes, so you know that nothing happened from the data acquisition to data pre-processing, etc. And at the end, you have it at the end of your pipeline. Unfortunately, this means that there's no real or potentially astrophysical continuous wave candidate left. So, as Gianluca already told you, we did our usual game of setting 90% confidence frequentist upper limits on the gravitational wave amplitude, which is this red curve here. I also show the blue curve, which is the Falcon or complementary Falcon pipeline for small electricity sources, and in gray, black, whatever, for pipelines of the LIGO collaboration. I think one important thing when one looks at like these upper limits is that actually these are quite different searches. Firstly, in parameter space, so I overlaid all of them, not really helpful, let's disentangle this a bit. There are really broad searches. This is like from 10 Hertz to a bit over 2 kilohertz, and you see at minus 10 to the minus 8 spin down to 10 to the minus 9, so really huge parameter space, where of course they suffer a bit due to the computational limitations. Then there are also like very deep support, breadth and depth approach or depth searches, where a lot of computational power is contained in a small region of parameter space to get more sensitive in that region. There are also kind of faster searches or robust searches, where by robust I mean allowing for small deviations in the waveform, like some spin wandering or so. And lately this is our search, which I think is sort of our middle ground. Plus we threw a lot of compute cycles at the problem to really get the best results in our parameter range chosen. Let me skip that. Where is he? I don't see him. Anyway, so you can talk to Gianluca about why actually our chosen range is quite good. He did a population synthesis study where we would expect neutron stars in our band to be now. And with the upper limits on the gravitational wave amplitudes, we can set the upper limits on the neutron cell ellipticity. Here, the ellipticity a bit more scary. So since I don't have any pulsars which I know of, I just pick basically some fiducial moment of inertia, some distance, and the frequency. And then with the upper limit, you can say, oh, okay, at 300 Hertz gravitation wave frequency, at 100 parsec or so, we can exclude neutron star ellipticities at the 10 to the -7 level, which is this millimeter mountain, which I always find mind-boggling. Same game with the R mode amplitude. Let's just skip this and come to the summary that we did a search for continuous waves from isolated unknown neutron stars in our galaxy. Unfortunately, did not have any detection, but set the most constraining upper limits in the search parameter range, and really consistently recovered these hardware injections with a high precision in nanohertz and frequencies 10 to the -15 and spin down in 0.3 arc seconds in the sky. With this, I thank you very much for your attention and I'm taking questions now.
Perhaps we have time for one very short question.
Eyes wide open approach. I mean, it's basically, I think, like one grid point. It's really eyes wide open. Why not?
Okay. Thank our speaker.